Learning Outcome 2, Algebra and Equations. 11.2.5a. Solve quadratic inequalities in one variable and interpret the solution graphically.
Hi, Deborah.
Hi, ma'am.
What brings you around to my class this afternoon?
Quadratic inequalities. Could you please give me some help again?
Yes, of course.
By the end of the lesson, you should be able to solve quadratic inequalities in one variable and interpret the solution graphically. Let's see what we have here.
To write a journal entry for homework explaining the different methods that could be used to solve this quadratic inequality. And I have no idea how to even start.
Well, it wouldn't be fair to the other learners if I helped you with this specific question. What we can do, though, is go over the different methods using other examples, and then you can apply that knowledge to this question.
That would be great. Thank you so much.
Pass me the textbook. Let me see if I can find another example here. Here we go. So tell me, how much do you remember about quadratic inequalities?
Well, I remember we have to factorize the trinomials first, but that's about all.
All right, so that is your first step. Why don't you start by doing that?
Okay. The trinomial is already written in standard form. I'll put down the brackets to start off with. Now, I need to find the factors of the first and the last term, which add to give me 5. So the factors are 1x and 1x for x squared, and 3 and 2 for 6. Both brackets have a minus sign in the middle.
Very good, Deborah. You've gotten very good at factorizing quadratic equations.
Thanks, I've been practicing.
All right, let's first talk about the difference between an equation and an inequality. When we are solving an equation, we are looking for a specific solution for the unknowns. When we are solving an inequality, we are looking for the set of solutions which satisfies the inequality.
So what you are saying is, in an inequality, there's a whole range of answers.
Yes, that's right. In a quadratic inequality, we need to find the set of solutions that make the inequality true. So in this example, we need to find the set of solutions that will make x minus 3 times x minus 2 greater than or equal to 0. Now, there are a few ways that we can do this. Let's start by using the table method. Have a look at the inequality. Would you agree that the inequality is asking for solutions of x that are positive or 0?
Yes, it says that the factors multiplied together must be greater than or equal to 0, and the values greater than 0 are positive.
Right, so in other words, we are looking for a solution where the two factors together will give us a positive or 0 answer. We already know from quadratic equations that if the factors multiplied together are equal to 0, either of the factors could be equal to 0.
I see where you're going with this. So, if the factors together are 0 or positive, we can find two of the possible solutions when the quadratic is equal to 0, which means that two possible solutions are x equals 3 or x equals 2.
Very good, Deborah. And we can use this to give us an indication of where the factors satisfy the inequality. We already know that the result is 0 at each of these points. This means that each of these points represents the point where the solution changes from positive to negative, or from negative to positive. We call these points the critical values. In order to solve the inequality, we need to investigate what happens on either side of these points. There are a few ways we can do this. To start with, we're going to try what is called the table method. We need to work out the solution for x minus 3 times x minus 2. So we will put this into our table. I'm also going to put in each of the factors so that we can consider them separately before we consider them together. We have already worked out that when x equals 2 or when x equals 3, the function is equal to 0, which satisfies the inequality. So I will add this to our table. I'm going to fill these spaces here with sets of possible solutions on either side of the solutions we already know. Here we have values less than 2. Here we have values between 2 and 3. Here we have values greater than 3. When we use this method, we aren't really interested in each and every specific value. We are more interested in the range of possible values. In order to determine this, all we need to do is find out whether the brackets give us positive, negative, or 0 answers.
Does this table represent all the possible solutions?
Yes, it does. And it includes the solutions we have already worked out. All we need to do now is substitute the values for x to find the solution that satisfies the inequality.
Let me give it a try.
Here we need a value for x that is less than 2. I'm going to use 1, which means for x minus 3, the answer would be negative. For x minus 2, the answer will also be negative, which means that the two factors together will give me a positive solution. When x equals 2, x minus 3 is negative. When x minus 2, I get 0, which together give me 0. Here we need a value between 2 and 3. I'll use 2.5, which gives me negative here and a positive here. If we multiply these together, we get a negative. When x equals 3, we get 0 here and a positive here. So the solution is 0. For the last column, we need a value bigger than 3. 4 is greater than 3, so I'll use that, which gives us a solution which is positive.
Excellent, Debuho. You've done very well. Now, looking at the table, can you tell me where the quadratic will be greater than or equal to 0?
Yes, when x is less than or equal to 2, and when x is greater than or equal to 3.
Well done. Now all we need to do is show our solution graphically on a number line. Do you think you can do that?
Absolutely.
Good work. Let's quickly go over the steps one more time, just to be sure that you are comfortable with this method. First, we need to write the equation in standard form. Then we factorize. Once we have done this, we can use the factor values to create a table, making sure that we cover all the possible solutions. Next, we complete the table by filling in the signs. Lastly, we give the range of possible solutions. If you would like to try this for yourself, here's a question just for you.
This method seems like a lot of work. You said that this was one of the methods. Is there an easier method than the table method?
Yes, there are 2 other methods you could use, but it is up to you to decide which method you find easier. Let's look at these other methods and then you can decide for yourself.
Okay.
This method is similar to the table method. This method also involves critically considering all possible regions of the solution. But in this case, instead of using a table to do this, we use a number line. I'm going to use the same example we used for the table so that we can compare the solutions. We are going to use the number line and only looking at the left-hand side of the inequality and use the values to help identify the set of solutions. As I explained before, the values are useful because they help us identify where the signs change from positive to negative or vice versa. We are going to pick a number in each region and substitute this into the left-hand side of the inequality to find out if the solutions are positive or negative in this region. Remember, the inequality asks for values which are positive or 0. We also already know that x is equal to 0 at 3 and at 2. I am going to mark those values on my number line with a closed dot to indicate that these values are included. If we wanted to indicate that these points are not included, we would use open circles to show this. Now, Deboho, can you give me a number less than 2?
How about 0?
That will do. Now, can you substitute that number into the left-hand side of the inequality and tell me if the solution will be positive or negative?
All right. If I substitute in 0 for x, I get a positive solution.
And can you show that on the number line for me?
Yes, I can show that by putting a positive here in this region where the values of x are less than 2.
Now we need a value in the next region, which is between 2 and 3. Why don't you try 2.5?
If I substitute that into the left-hand side, I get that the solution is negative. And to show that on a number line, I put a minus here in this region. Okay, now I need a number greater than 3. So I'm going to use 4 and put it here on the left-hand side. And I get that the solution is positive for this region. I put the solution here on the number line. Now I can see where on the number line my values satisfy the inequality. And all I have to do is put in the lines and arrows to show the solution graphically.
Don't forget to show your answer algebraically as well.
Oh yes. X is less than or equal to 2, and x is greater than or equal to 3.
Very well done, Deboho. You catch on quite quickly. As always, first we need to write the equation in standard form. Then we factorize and find the critical values. Next, we need to plot the critical values on the number line. Then we decide whether to use solid dots or open circles for the critical values. Once we have done this, we can check the regions on the number line and determine the signs in each region. And lastly, we give the answer range. Why don't you try this for yourselves with this example? Now let's have a look at the last method. This method uses your knowledge of quadratic functions to find the solutions which satisfy the inequality.
Does this mean we are going to have to use graphs?
That's right, but we only need to draw a rough sketch of the graph to find the solution of the inequality. In fact, what we are really doing when we solve an inequality is working out the region in which the graph of a quadratic function is above or below the x-axis.
That sounds really hard.
Okay, how about I show you this method first, and then you can tell me if it's difficult to do or not. What we need to do first is to look at the inequality as if it were a quadratic equation and draw a sketch graph of the function. When we factorized and solved for x, we found the x-intercepts of the graph. So we already know that the graph will cut the x-axis at 3 and at 2. Now, can you put those values onto a set of axes for me, Teboho? Remember, this is only a sketch graph, so you don't need to put in all the details onto the axes as you would do normally.
I'm sure I can. So I draw the axes and mark where x is equal to 2 and where x is equal to 3. That's easy enough.
Good. Now have a look at the inequality again. Is the a value of the quadratic positive or negative?
It's positive.
And what does that tell you about the shape of the parabola?
Does that mean it will look like this? Like a happy face?
Yes, it does. And now that you have the shape and the x-intercepts of the function, you have all you need to draw a rough sketch of the graph. Why don't you do that for us?
I've already marked the x-intercepts, so all I need to do is draw a parabola that is the right shape and goes through these points.
Good. Now have a close look at the graph. Can you see from the graph for what values of x the function is positive? In other words, for what values of x is the graph above the x-axis?
The graph is positive here, where x is less than 2. And here, where x is greater than 3.
And there you have your solution. All you need to do now is write it down. Remember that we need to include 2 and 3 in the solution because the inequality specified that we wanted solutions that were greater than and equal to.
Okay, so x is less than or equal to 2 and x is greater than or equal to 3.
Well done, Debuho. So tell me, now that you have graphed the solution, do you think it was difficult to do?
Well, actually, it was really easy.
Great. So let's go over the steps for this method one more time. As your task for today, I would like you to try Debuho's homework task 2. Write a journal entry explaining the different methods that could be used to solve the following quadratic inequality. 4x squared minus 4x plus 1 less than or equal to 0. Include your calculations in your explanation.